of thermal properties of matter. So in this lecture, we will revise thermal expansion. So what is thermal expansion? So it is a property that uh, that changes that occur changes in the body due to the increase in temperature, or you could say change in temperature. Means there is a change in dimension due to change in temperature. Then we have said the types of uh, thermal expansion. When we talk about types of thermal expansion, there are three types of thermal expansion. The first one is linear, the second aerial, and third is volumetric. Okay. Then we have said, okay, let me know on which quantities thermal expansion depends. So first we have change original dimension. The second is length, and third is material. Okay. So in this, uh, so first original dimension. When we talk about original dimension, you should know length, area, and volume. These all are dimensions. Okay. Then we have said when we talk about materials. Okay. So here we have assigned coefficients for different dimension and the different coefficient. Okay. For length, it is uh, and this coefficient generally known as coefficient of thermal expansion. Okay. And for length, it is coefficient of linear expansion. For area, that is beta, it is coefficient of aerial expansion. For volume, it is coefficient of volumetric expansion, and it's gamma. Okay, alpha, beta, gamma. Then we have said uh, we would now know what is the application of thermal expansion. When you want to know the coefficient, like sorry, uh, application of thermal expansion. So we have talked about two or three applications as like major application. The first is use of bimetallic strips in iron or thermostats, iron presses. As you have seen, if the press becomes so much heat, it generally on its own off. If you have think about it, so it is also the application. And the second is staging of wires within the uh, as like wire columns within as like within the tower, staging of wires within the as like towers, staging of electric wires within the towers. Okay. The third one was as like thermometer is also application of thermal expansion. Then after we have discussed relation between coefficients of thermal expansions in a isotropic condition. Isotropic means the density would be same dimension in every direction. Okay. So we have said alpha is equal to beta by 2 is equal to gamma by 3. Okay. Then we have did some derivations. First we have said uh, for anyone, uh, L is equal to L alpha delta T, because the delta L depends on original dimension, delta like coefficient of thermal expansion, and change in temperature. Okay. For L is equal to L alpha delta T. For delta A, for aerial change, it is A beta delta T. For volume, it is delta V is equal to V gamma delta T. Then we have discussed delta L by L type formula means it is also strain. So delta L by L is equal to uh, alpha delta T, delta A by A is equal to beta delta T, and delta B by B is equal to gamma delta T. Then we have discussed another type of formula, how you compute length final type of formula. Type final type of formula as like length final is equal to L in bracket 1 plus alpha delta T. A final is equal to A in bracket 1 plus beta delta T. And for V final is equal to V 1 plus alpha delta T. Okay. So here V1 plus alpha delta, here V in is initial, and the value we are computing here, it is V final. Then we have said, uh, then we have talked about what it was, mm, what we have talked about, yeah, for cavity type of questions. Sorry. Then we have talked about stress and strain type of how you will relate this thermal expansion properties with uh, thermal properties of solids. As you know, if you could relate it. So here delta L by L is equal to alpha delta T. So here delta L by L is equal to strain. So strain is equal to alpha delta T. So I have said, hey, compute stress. Then you in your mind, hey, stress is equal to y times string. So here you could multiply y into alpha delta t, alpha delta t. Then we have said, hey, compute force. So you say force is equal to pressure into area, and pressure is equivalent to stress. So stress is equal to, here we have seen, y alpha delta t multiplied with area, that is y a alpha delta t. Then we have said, hey, delta volume, in case of volumetric, we have talked about in the case of length. Then it is also in the case of, same in the case of volumes. So when we say a string or delta by v, delta v by v, it is what, it is, as we have seen, delta v by v is equal to sorry, delta v by v is equal to gamma delta t. Okay, so I have said, hey, compute the pressure, sorry, compute the force. Force is equal to pressure into area. And you have said, hey, I could compute the pressure, that is stress, and I could compute the stress by multiplying beta, uh, beta times of stress is equal to what, stress is equal to beta, any bulk modulus into strain. So if you multiply stress, if you want to compute stress, it is bulk modulus times of delta b by v, and that is gamma delta t. Okay, so here, if you want to compute force, that is pressure into area, that is uh, bulk modulus into gamma delta t into area. Okay, similar. Okay, then after we have talked about the cavity types of questions. In this cavity types of question, there are two conditions. The first one is, uh, in this condition, we take two materials and adjoin them. Okay, in the, in within and in okay, sorry. In this condition, there are two conditions. Okay, in this type of question, there are two conditions. The first is the two materials that we have used that have same matter, there are same material, and the second, two materials are different. Suppose I have taken the wheel and I have joined another wheel within it. So if their two materials are same, they will expand, and their hole will be, their inner hole also become, their inner hole also expand. Then we have talked about, if material is made of more than two materials, in the first condition, if outer one material is have more alpha, or you could say it has more coefficient thermal expansion, and inner one has less, then uh, the inner hole will expand. But in the condition when the outer material uh, has less thermal expansion coefficient rather than inner one, as like inner will expand more fastly, so it's what would happen, its inner hole will become reduce, inner hole will reduce. Because why? Because it, as like inner material is not getting the place to expand, so it will expand rightly, as like in the inner side. If it's not getting the side to expand in the outer side, it will expand in inner side. Then we have talked about a case in which, if we have taken the two rods, as like L1 L2, that's there's coefficient of linear expansion is alpha 1, alpha 1 alpha 2, and we have increased temperature by delta t1, delta t by delta t by similar temperature. And if we have said, if we have taken the same, if we have taken in the second situation, if we have taken a length of L1 plus L2, and their linear coefficient is alpha 3, so compute the relation between alpha 1, alpha 2, and alpha 3. Then we have said you can compute the relation, uh, as like by if there, as like the change in length would be same. Okay, as like if you what the situation was there, in the second situation, the change in length was similar as compared to the first and second one, as like delta L3 was delta L1 plus L2. Then we have computed the relation, that was alpha 3 was L1 alpha 1 plus L2 alpha 2 by alpha L1 plus alpha L1 plus L2 divided by L1 plus L2. Okay, then we could compute the uh, thermal expansion by this.